Welcome back, everybody. So let's continue. So I have shown you all these complicated terminology, but basically, again, it's a 2x3 grid, right? So we can have processed, non-processed, and then tied with position, tied without position to documents. Okay. So now the next thing that I will show you is something that is commonly done in many systems, especially Boolean querying systems, even though that has to be put in the context that it was long ago and we didn't have the space and the resources that we have today. So we had to be a bit more careful about the disk space that the index is going to take. And for this reason, there was an optimization that was commonly done, and it's to look at the standard inverted index and to notice that some of the terms on the left of the index have a lot of postings. Sometimes even almost all of the documents are in the list, right? So words that appear in almost any documents. Can you imagine some of the words that could appear in any documents in English? N, yes, exactly. N, V, A, is, B. So all of these words that are very frequent. And in fact, if you search for these words and they appear in any document, that's totally useless, right? Because they are anywhere anyway. So why don't we just drop completely the term from the index and ignore it? If it appears in the query, we don't even bother. We just throw it away. It is an example. B is to. So these are such terms that we want to ignore. And so these are called stop words. Okay? Stop words. Here's actually a full list. There's somebody in the waiting room. A and R as at B by for from. So all that's a common list of that is called Reuters list that was popular at some point. Now there is a trend, and again that has to do with the fact that we have larger and larger disks and more computing power. And the trend is to have less and less stop words. So back then, we could even have large lists of hundreds of stop words that we completely ignored. And now the trend is even no list at all. If you look at a search engine like Google or Bing or DuckDuckGo, typically, they will not bother with stop words anymore, right? So we'll see that an engine like that is just not a Boolean. It's not just a Boolean engine. It has a lot of very different and complementary querying mechanisms. But basically, it's a trend that is slowly disappearing, this stop words things. But historically, it's important to know that it's there, and that is a good optimization to do. That saves you both space and time, because you have to actually traverse this posting list at runtime. So if you get rid of such a large list, that accelerates the query. Who is with me? Okay, very good. Okay, so that's number one, first optimization we can do. Then there is another one that is related to the notion of type versus token when we have this processing phase. And what might distinguish a token from a type is that we group, that's one of the ways to do it, we group the tokens into types. So what I mean here is line number 3 and line number 3, line number 6. If you want the precise wording, it's a non-normalized type that we turn into a normalized type. And the way we do that is that in here, I have a non-normalized type, and together I put them in a box, and that is a normalized type, right? Here again, non-normalized type, non-normalized type, non-normalized type, and we normalize them, and that is now a new normalized type. Today, that probably comes from the 19th century, and today, again, non-normalized type, we group them together, and now we have a normalized type. The same here with Zurich, and so on, right? So all of that, the same normalized type. And by the way, I explain it from here to here. But again, when you go from a non-positional token, that becomes a non-positional posting after you have done this grouping, right? A positional token becomes a positional posting when you do that. For whom is that clear? Right? So what I'm saying is really the difference between this raw and this processed part, one of the ways is by doing these groups. You know that mathematicians call these groups equivalence classes. Normally, you studied that in discrete math, right? Relations, equivalence relations. And the nice thing about an equivalence relation is that it allows you to group the stuff into packets that you call equivalence classes, and then you can use the packets instead of the original items. And so that's what we do here. Normalized types are basically equivalence classes of non-normalized types. Okay. And in order to create these groups and to convert a non-normalized type to a normalized type, you can apply some rules. And the rules have been figured out over several decades. It's a bit of a trial and error thing. People try it and they see how good it goes. And then any engine can use some of the rules, maybe not all of the rules. So it's really some fine-tuning and tweaking, right? There are rules, for example, that just remove characters. I showed you it's not that trivial, but for example, USA with dots, you remove the dots. Today with a dash, you remove the dash, right? Again, it's not easy. You've seen all the counterexamples that show how complicated it is, but there are rules that do that. Then there is another approach. This approach is asymmetric. You know that when you have an equivalence relation, it has to be symmetric, transitive, and reflexive, right? These are the three for an equivalence relation. But it is symmetric. If A is in the same group as B, then B is also in the same group as A. So that makes it simple because in that case, we just replace the non-normalized type with the normalized type. We replace an item with its group. But there is another approach that is not symmetric. It has rules like this that process words into other words, but not in a way that works the same in both directions. For example, Windows with an uppercase, you might assume is the operating system. With a small, with lowercase, maybe you might want to include maybe the uppercase in case it's at the start of a sentence. You might include the singular form. If it's the singular form, you might include the plural form. So it's not symmetric because it doesn't go both ways. And that is called an expansion. So it means that whenever you see a specific word, you include other words that are related. There are two ways to do that. Let me do it with lift and elevator. Imagine that somebody is looking for lift. Maybe they also want to see documents with elevator, right? So in that case, you can do one of two things. The first thing is that when you build the index, so at the very beginning, before even anybody queries anything, you build the index with lift and elevator. Maybe lift was in document 1 and 5, and elevator was in documents 1, 4, and 6, right? And you do what's called an expansion. So if you have this rule, lift to elevator, and maybe you also have elevator to lift. I took here a symmetric example that doesn't have to be. You expand here. Lift will also give you 4 and 6, and elevator will also give you 5, right? That's called an expansion. What it makes happen is that if the user says lift, that will also return documents 4 and 6. That's called an expansion on the index side, index expansion. But there is another way to do exactly the same thing. It's to keep the index as it was. We still have the index with the actual lift and elevator happening, appearing in exactly these documents. And we have this index, but it's when the user queries that we expand the query. And in the query, we rewrite it as lift or elevator. It has the same effect. It's going to return documents 1, 4, 5, 6. Who is with me? Right? So it's asymmetric because you have A leads to B, but it doesn't have to be that B leads to A. And you can either do index expansion or query expansion, which leads me to a question. Of course, I'm going to, after so much time, probably get an error. Ah, no, just this screen. Okay. Which statements are correct? Index expansion takes more space, but queries are faster. Index expansion takes less space and queries are faster. Query expansion takes less space, but queries are slower. Query expansion takes less space and queries are faster. So index expansion, that's the left of the slide, and query expansion is the right of the slide. Yes, exactly. And what that teaches us is something you already know. There is no such thing as a free lunch in computer science. Space or time, you can't have both. So either you're going to save on space or you're going to save on time. So indeed, in the case of index expansion, it takes more space. That's the cost for the queries being faster. And query expansion is going to be taking less space. So here you win. You need less disk space. But the cost for that is that the queries are slower. Right? In fact, there is a free lunch in big data with the clouds. But that I leave as a cliffhanger. But otherwise, generally, there is no free lunch. Was it 3 or 4? I think 3. I already knew that's probably 4. Let me try 4. Okay. Let me try again. Aha. Give me a minute. I'll try to debug that. Somehow, either Zoom or PowerPoint refuses to work, and I need to figure out which one it is. It's good. It gives you a bit of a break. There you go. It's back. We are back. Okay. So technique number 1, equivalence relations. And we replace the items with the groups, meaning that we replace the non-normalized types with the normalized types. Technique number 2, expansion, not necessarily symmetric. Whenever we see a specific non-normalized type, we just expand it to more of them, right? But of course, if you do the asymmetric fashion with query expansion, then you don't have any such thing as normalized types because you don't have equivalence classes, you don't have groups, right? So in that case, you stay with the original non-normalized types. You just expand. Okay. Now, coming back to normalization, in the case of the equivalence classes, in order to make it work, one thing we can do is also remove accents, also called diacritics, right? So cliché, Zurich without the umlaut, or we add an E. You know that in German you can add an E. U is UE, A is AE. Of course, it works in High German, but not in Swiss German. Like gut is not good, especially in Wallis, maybe gut, but it's complicated, right? But anyway, parenthesis closed. We can just remove the accents in this way. And these are yet other examples with lower casing. True casing is uses some machine learning. That's to figure out if it's apple, for example, is the brand apple or the fruit apple. And so in that case, you can either keep the uppercase or not keep the uppercase, right? Again, I keep saying it, it's complicated. That's my main point today. Now there is a technique, another one, to create these equivalence classes that is very popular, and that is called stemming. Stemming is a way to build these equivalence classes in a way that is purely mechanical, algorithmic, and rules-based, without even understanding anything. There's no machine learning, there's no artificial intelligence, absolutely nothing. It just takes a word that is made of characters, and it just modifies it in such a way that it creates your equivalence class. For example, analysis is transformed to analysis. Of course, it's not an English word anymore. That's your equivalence class. Feature into feature, R, easily, and so on. So you basically chop letters of the words, and then different words might give you the same chopped version, then they are in the same equivalence class. The most famous one of these algorithms is known as the Porter stemmer. It is really incredibly simple. It's just very large, but it is simple. It's just a bunch of rules that tell you how to do these transformations, right? So this is an example. It's only a subset of that. It's a very long list. And it just gives you, like, whenever you see this, change it to that. And you apply the rules without thinking, just one by one, all the way. And that is going to transform the words in these equivalence classes. And when you do that, you get something like this. So there are several versions. Let me explain what we have here. This is the original text. This is the one you can understand. Well, maybe PhD people in biology can understand it better, but at least we can understand the words. This is the version with the Porter stemmer, right? If you take every one of these, let's call them positional tokens, because we see them in the text, and we replace them with the output of the Porter stemmer, it's one-to-one, right? Search becomes search, and becomes an, analysis becomes analysis, and so on. It's one-to-one. That's what we get with the Porter stemmer. And what you get out of that are the normalized types that you can use to build your standard inverted index, right? This here, Lovins, is just a different algorithm. It's the same thing, does exactly the same thing, but it just uses different rules. That's called the Lovins stemmer. And here we have the Pace stemmer that uses yet a different set of rules. Okay, so they are competing, right? Different algorithms, but this is one way that is, again, very easy to implement because it's just about going through the rules and applying them, and that give you the normalized types that you can use for your index. Okay. Stemming works really well in a language like English. Works really well. And in fact, do not try to use these stemmers on German or French or whatever, it will not work. That is made for English, right? Really specifically for English. For languages like English or Italian or Hindi or many others that have a lot of conjugation, it's a bit more complicated because here you need to be a bit more aware of the language. And so there is this so-called Vauquois triangle in the levels of abstraction, where here you have the actual words. So this is what we are processing, right? Reading from the collection. And then you can go higher into syntax or in semantic, or the holy grail of everything, this interlingua. And in fact, with LLMs, we are kind of getting really close. But anyway, that has always been a challenge. And so for these languages that have conjugation, then instead of stemming, we use lemmatization. That is just a different way, it's aware of the language. Lemmatization, if we did it in English, would mean that, for example, computer, compute, computes, computed, computation, computing, these are all the same group. You put them all in the same equivalence class. That's the same normalized type. But the reason we know they are is because we understand English and we understand the structure of the language, right? And the same goes in these languages. This is especially useful for all these languages that, well, this is not a language, it's several languages, but this is very useful, French, Spanish, German, when we conjugate. Even though you can do it in English that doesn't really help much. It's really the stemmer that is more helpful, right? So English, use the Porter stemmer. German, Italian, Spanish, and so on, then use lemmatization by being aware of the conjugations. Whom is that clear? Right? Okay. But if I summarize again, it's complicated. This is my main message for today, that it's absolutely not as simple as it seemed last week. Now, I'd like to talk to you a bit more about tokenization, meaning that we rewind to what I said at the start, no longer at the words or trying to group them, but where do we cut between the tokens? Where do we put the limits? In the example I gave you, we just use the spaces, right? In an improved version, you use also the punctuation, the dashes, and so on. But basically, you have these very simple rules, and you just cut between the words based on the spaces. So it's very, very highly driven by the space character. Now, if you remember the fun time we had with languages, in German with these Donau-Damm-Schiffards, blah, 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 or in Siberian Yupik or Turkish or all the languages where you assemble words together, you cannot do that. It's not enough. You can just rely on the spaces and tokenize in that way. So this way has its limits. Now, we learned a lot about more modern forms of tokenization with the large language models in the past few years. And the way that a large language model is tokenizing is basically language neutral. It's not language neutral in the sense that it doesn't change at the end, because that depends on the training set, but it is in the sense that if you do it like in that case, we have managed to tokenize for English. So that would be the Shakespeare, the way that it's tokenized by ChatGPT 4o, DeepSeek, Llama. So this is the tokenization. And I did the same. I use this app here that you can use. I use the same for Swiss German. And now you see it's also able to tokenize. So of course, the tokenization now you see it's not based on the spaces anymore, right? It's a bit more complex. But what I mean with language neutral, maybe it's not the best word to describe that, is that this is why ChatGPT can speak Swiss German to you. Because the tokenization process was done with different algorithms. And so it can basically be applied to many. I tried it with Hindi too. It's perfectly capable of telling you a lot of things in many languages, even with different characters. And so I'd like to explain to you how all of that is actually working, and how can it be that having processed a lot of documents, we are also able to tokenize pretty much any language, and you could even put Siberian Yupik in there, or the Donau-Damm-Schiffards and so on. It will just tokenize it, right? Even if there are no spaces. And so I'm going to give you an example. And the learning, the lesson that you should get out of this is, you've seen on social media, right? People make fun of ChatGPT because it cannot tell you how many R's there are in strawberry, right? You've seen that one. This is why. It's because of tokenization. It cannot possibly know that because the tokenization, the way it's tokenized is basically in the way. So here's an example of a tokenization algorithm that is known as byte pair encoding, BPE. There are variations of that are used for LLMs. There's slight differences between them. So I took a very simple one, the original one, and I'm going to explain how it works. In order to keep it simple, I just took an alphabet with 2 letters, A and B. right? But of course, it generalizes very well to more letters. And I just generated, in that case, just a random string of A's and B's in here. I didn't even put spaces. A space is a character like any other in that respect, right? So just A and B. So it's a sequence. I put it on 2 lines, but it's really just 1 string. Now, the way that we do it in ChatGPT, that's a variation of BPE already, is that we set a target vocabulary of 6. Right now, if I would very naively tokenize every character gives me 1 token, I obtain a vocabulary of 2 terms. There's term A and there's term B, right? Vocabulary with 2. So I'm going to set a target vocabulary size, right? I think for ChatGPT, it's typically 100,000, the vocabulary size that you want to achieve, right? But here I'm just picking 6 so that it fits on the side. So we are going to just expand the vocabulary with 4 more tokens in such a way that we get 6 in the end. And in order to do that, I'm going to look at the pairs of adjacent tokens. That's why it's called the byte pair encoding. So I run some statistics, and what I found out is that there's 12 occurrences of AA, 7 occurrences of AB, 7 occurrences of BA, and 5 occurrences of BB, right? If I made any mistake in counting, just let me know and I will fix it, but that's the idea. And so what I observe here is that the most frequent pair of adjacent tokens is AA with 12. So what I'm going to do is I'm going to create a new token, AA, that I add to my vocabulary. So now I have 3, A, B, and AA. And I will replace and merge these AA tokens when I see them in the documents. So you see, this is what happened. I'm adding this term, yes, it's a term in my vocabulary. It's a new term that I call AA in there, and that gives me a vocabulary size of 3. And then I do it again. I again look at all possible pairs. Now there's 9 possibilities, 3 times 3, because I have 3 tokens. And I did the statistics all over again, right? So you can see AB, for example. You can see 1, 2, 3, 4, 5, 6, right? So I put it 6 times, and then I did it also with the others. Notice that AA is a single token, so BAA is a pair. It's the pair with B and with AA, right? A pair of these 2, 4 times and so on. So now I iterate the process over and over and over and over again. What is the pair that appears the most frequently? And that's AB 6 times. So I'm going to create yet another token here, AB, and I replace every occurrence of AB with that new token, right? So you see what's going on here is that the number of positional tokens in my documents is decreasing or increasing? The number of positional tokens. Is it increasing or decreasing? Who thinks it's increasing? Who thinks it's decreasing? So the majority is correct. It is decreasing because every time I keep merging them. So whenever I merge them, that's 1 less token because I replace 2 tokens with 1 token. So we have less and less and less tokens in the documents. This is why this algorithm originally was sold as a compression algorithm, because you can compress the size of the documents. Every one of these tokens can be replaced with a number. A would be 1, B would be 2, AA would be 3, and AB would be 4. And then you can encode the documents just with the ID of the token that you have. And the more you do that, the more you're going to compress it because the number of these integers, the number of these tokens is going to go down and down and down. But the price to pay for that is that you need to maintain a vocabulary and the mapping with the integers somewhere else, right? So there's always a cost somewhere else. Who is with me? right? Very good. So byte pair encoding. But again, here, applied to ChatGPT, we have our target vocabulary size, and we only have 4, so we need 2 more. Let's do it. I do my statistics all over again. And here, the winner is AAAB, 4 times. You see it 3 times on the first line and once on the second line. Do you see them? 4 times. So I'm going to, again, create a new token, AAAB, and I replace them. I use my colors here. And now I have a vocabulary size of 5. And now the number of tokens has decreased again, right? So now I need 1 more. So I again run my statistics. And do you see the winner here is AAAB, B. That's my winner. It's still a pair, right? Because AAAB is a token, token number 5, and B is another token, token number 2. So the winner is 3. I use now yet another color, brown this time, AAABB. And now I have even less tokens. And now I stop because I have reached my desired size of 6, right? So this is one of the differences with the original algorithm, because the original algorithm tried to be optimal in the sense of the compression. But here we are building an LLM, or at least that's the context. So we just want to target a specific vocabulary size. And again, for ChatGPT, typically 100,000. Yes? This is because I took this example and it's very small. The fact. So let me repeat maybe for the people on Zoom. You basically notice, and you're absolutely correct, that now the token A is not used anymore. And what I was saying is that that's because I took a very simple and small example. So that's really just a coincidence here with my example, that in real life would probably not happen in this way. The other thing I want to say is that what we've done here is on the training set. I took my input collection, the training set, and built the tokens in this way. But now we are going to get user inputs. We might need to tokenize with this vocabulary. We are going to tokenize incoming documents. These documents might still have an A in there when you tokenize them, right? So just because in that very specific example, the A disappeared, doesn't mean that it disappeared from the vocabulary, right? It's still there, and we are still going to see this token, right? By the way, I use token and term interchangeably here, but that's because here I just forget about everything that is in between, right? I'm directly assuming that I tokenize, and there I have my index, but you know that there's all the steps in between. All right. So does that answer your question? Yeah. All right. And so now, as I said, we have incoming queries and incoming documents. So let's say now we have this vocabulary, and we have now this prompt that a user has just sent us, and we need to tokenize it. What we do is we go through the same order in which we had previously built the vocabulary, and we just tokenize. So A, B, now AA. So all the AAs, I basically replace them, right? Now AB, I do the same. AAB doesn't exist. Actually, I'm done. AAAB, AABB, for that specific document, I will not find. Do you see that in that example, there is an A? It's still there, right? So this is why I'm saying the vocabulary size is still 6, even though it disappeared in the former documents. Do you see the number of tokens? 32, 29, 21. So we compress. We lose the number of tokens. And so with this algorithm, now I'm coming back to what I showed earlier. This is the reason why you can tokenize in this way, regardless of the spaces, and based on that algorithm. Now you see ChatGPT 4o, DeepSeek, Llama, they don't do it in the same way because they have their own cooking, right? You have the basic recipe, and then everybody is just improving in this or that way. We will see later when we study language models at the end of the semester that you can have variants of this algorithm, that instead of doing it in this way, we try to optimize entropy, or we try to optimize some probability of generating a document. So there's different ways that give different results, but the idea is the same. We create tokens in such a way that we can tokenize absolutely any input, even something completely unknown, and we'll always manage, right? But If your training set was highly focused on English, you might get something that looks more like this. So here, it seems that it's close to the spaces, but not always. Do you see the possess on the bottom left? That one is cut into 3 tokens, but most of the words have just 1 token. And Swiss German, which might have been a bit less present in the training set, we can still tokenize it, but here you see that it's not just as simple as using the spaces. And what's more, imagine that now we get some completely new language we've never seen before. Maybe some extraterrestrial signal received from space, and we just got the bits. Well, the nice thing is that you can also apply tokenization to UTF-8 or at the byte level. You don't even have to have an alphabet or anything. Anything that is a sequence of bits, you can apply these algorithms. So that makes them highly forward compatible with the things that you have never seen before, and you can still handle it in there. Okay, who is with me? All right, so I wanted to show that to you. Again, you'll get much further into the LLM course if you take it later on. But I wanted to show you that, and that in fact kinds of short circuits the whole thing with stemming and lemmatization and all these things, because now we have this more flexible way of doing things, and then you feed it into some neural networks to make it work. All right. Is there a question on Zoom? Oh, from you.
Yeah. Like this example that you presented here, like with the full vocabulary, if you go to the next slide, I think it was with the full.
Yeah. Do you have the microphone, by the way? Do people hear you? Yeah.
Yeah, with that vocabulary, there may be more than one ways to tokenize this sentence, but is there like a strict heuristic that we have to follow to tokenize it with the given it, or?
So here, that's exactly why you have all these variations. There's more than one way to do it. Here, the way we did it was just left to right flat, meaning that we go left to right, we accumulate statistics on the tokens. One example where you can see, you could claim it's arbitrary, is that I had a triple A here, and we tokenize with AA and then a single A, but you could also do it the other way around. So you see there's all kinds of variations. So that is the first rule that I used in here. And the second rule is that when I create my new token and look for the winner, I do it in a flat way. It's recursive, but it's flat, meaning that I look at all the pairs and I don't care if it's a pair of 1 character token or 2 characters token, I just do all the pairs. There are variations of the algorithm that keep doing it on only the first level tokens and then create second level tokens. And after it's done, then they start including the second level tokens in the statistics and create the third level tokens. That would be a layered approach. That's yet another alternative. Here, I just kept it simple and brute force, right? I just kept looking at the pairs, kept looking at the winning pair, and kept creating a new token. So you're absolutely correct. There is not a unique way to do that. There's all kinds of variations. And that's exactly the reason why you get here this variety of tokenization, because there's not just one way. Right. Okay. All right. So what do we have next? Oh, skip lists. Do I still have time? Yeah, I think this one I still have time for 5 minutes. Now I'm going to get back to the standard inverted index, and where we execute a query and try to compute the intersection of 2 lists, because we had an AND query, right? So it's an optimization. So remember the postings and the standard inverted index. Remember the intersection algorithm. You used it in the question I asked you earlier, so I know you know how to do that. So here, let's do the intersection of A and B based on that example. Right? So it's this PowerPoint karaoke that we did last time. So you see 1, 1, that's the same. Then 2 is smaller than 3, so I move it. 3, 3. Then 4, smaller than 10, so I move forward. Then 5 is slower than 10, so I move forward. Then 6 is slower than 10, so I move forward. Then 7 is smaller than 10, so I move forward. Then 8 is smaller than 10, so I move forward. And 9 smaller than 10, so I move forward. Then 10 is equal to 10. Now I wake up. Okay, 10, 10, 11, 12, 14, and so on. Did you notice something here apart from the fact that maybe you fell asleep while I was doing it? Did you see this long sequence of non-matches? There was a very long sequence, 4, 5, 6, 7, 8, 9, that didn't match anything. Because here we have a list that's very long compared to a list that's actually much shorter. And so can we do it faster? Obviously, the answer is yes, because I wouldn't be telling that to you. And the idea is, what if we had a magical pointer that we basically see originate at 4, and that tells us out there, if you take that secret path, there is a 10 that directly jumps to the 10. Do you see that if we could somehow use that magical pointer, that would save us all the comparisons? We could directly go there to the 10 and continue from there, and that would be faster. Who agrees with that? Right? Well, these magical pointers exist. Oh, is everything okay? So these magical pointers do exist, and they are called skip pointers. We call them skip pointers. So this is little structures that we add on top of our postings list in the standard inverted index, and that provide us with the shortcuts. It's like some sort of highway that that gets you faster to other postings down the line, right? In fact, this is part of some more complicated data structures that augment linked lists. You can even have multiple layers of these things. But now I am just showing you one layer with the skip pointers. I have only 3 minutes left, so I will continue that tomorrow. So we have the skip pointers, but I will ask you not tomorrow, Saturday, no, next Friday. I will ask you what should be the length of these skip pointers. What do you think should be the length of it? So I'm going to stop here and just ask you, if you understood what I've been telling you today. Oh, what happened? It's just not the right one, this one. Yeah. So you know, you can slow me down, you can accelerate me, just to get a feeling. That looks great. Awesome. For the 4 people who understood everything, 3. For the 3 people that understood everything, I recommend an optional extra exercise that you can do for yourself. Try to implement this tokenization algorithm, the BPE, on top of Shakespeare, for example. You take the Shakespeare corpus, try to implement it. Can be fun, right? But we are not giving it as an exercise to everybody, because we try to have this rule that every week there is just one practical exercise, because otherwise it would be too much. But yes, if you understood really everything and you want the adventure, then 4 now. So I motivated somebody else to do it, right? So try it. Thank you very much. I hope you enjoyed today's lecture. Enjoy the exercises on Boolean querying. You'll have your first prototype of information retrieval engine. And I will see you next week at 10 a.m. for week number 4. Thank you very much. Enjoy your meal.